Well, good afternoon, everybody, and it's my pleasure to be here joining you virtually this afternoon to discuss this Mistastin Lake, or Kamestastin in the local Innu dialect, a unique meteorite impact structure up here in northern Canada. Okay, so I think probably most people in the room are familiar with this document. It's the Science Definition Team report for Artemis 3, and I just pulled a couple of sentences from it that talks about, well, the fact that it talks about astronaut geology training and the importance of it, I think is fantastic. We really want our boots on the ground to be well trained, just like we did for Apollo. And the wording here is also specifically tailored to the Artemis program to maximize the value of this unique lunar environment. And of course, when we look at the moon, unlike the Earth, the moon is really dominated by two main geological processes, and for most of its period of existence, really one dominant geological process, which is impact cratering. The moon has literally been pummeled for 4.5 billion years by asteroids and comets, such that there are thousands upon thousands of meteorite impact structures, from giant impact basins to tiny micrometeorite pits a few millimeters across. And of course, most of the samples that we brought back, and there's one down there on the bottom right, will be either impactites or impact breccias, impact melt rocks, or in some way affected by meteorite impact. And when we're doing field work on the moon again, this challenging terrain, much of the topography also comes from meteorite impacts. And again, unlike the Earth, much of the outcrop, most of the boulders that we will encounter, or a big majority of them anyway, are on the surface and exposed for us to study by this impact process. So if we look back to Apollo, the Apollo missions went to a huge variety of sites, predominantly in the continental US, a few overseas, but literally a few dozen different sites to learn about geology and then specific geological processes. Out of that large number of sites, they actually only visited 3 meteorite impact craters. All of the missions went to Meteor Crater in Arizona, and that's where we've been taking astronaut candidates back again for the last couple of classes. Apollo 14 then moved on to something bigger, the 24-kilometer diameter reef structure in in Germany, and then the substructure, which is in northern Ontario, was visited by Apollo 16 and 17. Now, a lot has changed in our understanding of impact processes and also in the number of sites that are available for doing training. Back during Apollo, there was a small handful, maybe 3 or 4 dozen confirmed impact craters on Earth. We now know of 201, and they are all portrayed here on this image. And here in Canada, we have a great long list of very famous and well-exposed meteorite impact sites. So the next speaker will be talking about one, the highest cross up here on Devon Island. I'm going to take you down to Labrador, slightly further south in the Canadian high Arctic, to this Mistastin Lake impact structure. So it's relatively young, geologically speaking, at about 36 million years old. It has a diameter of about 28 kilometers, which puts it into this complex crater morphology class. The right-hand side there is a Landsat image. The crater rim, if you can see my mouse, will be out here. It's fairly eroded, glaciated, but you can see a central island in the center. And then some key things is that there is some fantastic outcrop of impactites, so rocks produced by impact events. And this bottom left image, this outcrop is about 4 meters high. We have various types of breccias, impact melt rocks, and complex relationships. The other big unique thing about Mistastin is its target rocks. It formed to a large part in anorthosite, which is this rock present in the lunar, or dominant of the lunar highlands. And Mistastin is one of only 2 or 3 impact craters on Earth with any portion of anorthosite. And it's the only crater where most of the melt rock is derived from melting anorthosite. If you take into account gravity, Mistastin actually scales pretty well for Tycho. And put in these 2 images aside, we have this preserved central peak at Mistastin. The lake now occupies most of the crater floor, but we do have outcrops along the lake margin, and then we have this collapsed crater rim for comparison. So zooming in, we're in this unique part of Canada where we're transitioning from the boreal forest up into the tundra environment. And so most of the terrain is quite bare and barren. On some protected hill slopes, we do have some vegetation and trees. This goes to show some of the outcrop. This is actually one of the most probably iconic outcrops of any crater anywhere on Earth. This is so-called Discovery Hill, and what you're looking at here is an 80-meter high cliff of impact melt rock. And if you've got good eyes and the screen's good enough in the room, these vertical joints are actually columnar joints. And so, this is a textbook case of an igneous rock produced from hypervelocity impact. If we zoom in and look at some more of the features, this is actually also on Discovery Hill. So it turns out this is not the impact melt sheet, the crater fill that the original workers thought, but this is actually more akin to the melt ponds that you see in the terraced region of lunar craters. And here are actually two astronauts, Josh Kutrick and Matthew Dominic, standing further around the corner of that previous scene. And literally, you can almost put your finger on the contact between two different types of ejecta deposits. And so this really provides a unique opportunity to study these deposits up close. We see a variety of impact melt textures, which is going to be important for the astronauts to get familiar with. Just within one crater, there's my hand in the background on the right-hand side for scale. There's, quite long laths, crystals of plagioclase. And on the bottom left, you could be forgiven for thinking this is somewhere in Hawaii or Iceland, but this is a nice vesicular andesite by composition. But in this case, it's an impact melt rock. So lots of really unique rocks that are, in some cases, like these two images, quite hard to differentiate from, volcanic rocks. And so this is a challenge for us here on Earth. It's going to be more of a challenge on the moon, where we typically lack outcrop and context. And so getting our astronauts familiar with these types of rocks can be uniquely done at Mistastin. So this is also a fantastic outcrop. Didn't have enough time to show you the context for this, but it's a long river section, a few hundred meters long. And these are the ballistic ejecta deposits of Mistastin. And everything you're looking at here is an orthosite. And so there's an Apple pencil for scale in the image. And this white granite-looking rock that is white is an orthosite. And here you can see, hopefully, the fragments, the clasts, larger clasts of an orthosite in this finer grain ground-up matrix. And so, if we were able to access a relatively fresh, well-preserved ejecta blanket on the moon in the highlands around the South Polar region, it could and should look just like this. Just to wrap up, one of the other interesting things that we've been bringing into astronaut training at this and other sites in the Canadian Arctic is that there are a lot of similarities in the challenges, obviously, relatively speaking. The Arctic is expensive, lengthy travel times, difficult logistics, narrow window for field work. And also it's a remote and harsh environment. And so, this also gives us the opportunity to put the astronauts in a challenging environment in a small team where they can practice expeditionary skills as well. And so for team building and overall expeditionary skill development, these Arctic sites can also combine that aspect of astronaut training too. And I think that is my last slide, and I might have maybe 1 minute for any quick questions now, or we can leave them to the end. Thank you.